On April 17th, 2026, engineers at NASA's Jet Propulsion Laboratory in Pasadena, California, sent a command out into the darkness of interstellar space, a single instruction traveling at the speed of light toward a spacecraft now more than 15.8 billion miles from Earth, so far away that the signal itself needed nearly a full day just to arrive. The instruction was simple, and in its own quiet way, heartbreaking. Power down the low, energy-charged particles instrument. For almost 49 uninterrupted years, since the moment Voyager 1 first left Earth in 1977, that single device had been continuously measuring the ions, electrons, and cosmic rays swirling around the spacecraft as it crossed the solar system and then kept going past the orbit of every planet, past the edge of the sun's protective magnetic bubble, and out into the truly empty gulf between stars. It had helped scientists map the structure of the interstellar medium itself, the thin, mysterious soup of gas and radiation that fills the space between star systems, territory no other operating human spacecraft has ever directly sampled. And now, with a single radio command, it went silent, one more casualty in a slow, irreversible, entirely predictable countdown that has been running since before most of us were born, a countdown NASA engineers have been fighting, watt by watt, for nearly half a century. And one that is now, in 2026, entering its final and most desperate phase. To understand why a single dying instrument on a 49-year-old spacecraft counts as genuinely dramatic news, you first have to understand exactly what Voyager 1 is, and exactly why NASA never built it a way to simply recharge. When Voyager 1 launched on September 5th, 1977, just over 2 weeks after its twin, Voyager 2, lifted off on August 20th of that same year, its original mission was relatively modest by today's standards. A close-up tour of Jupiter and Saturn, taking advantage of a rare planetary alignment that occurs only once every 176 years, allowing a single spacecraft to use each planet's gravity to slingshot toward the next. Voyager 1 flew past Jupiter in 1979 and Saturn in 1980, returning images and scientific data that fundamentally reshaped humanity's understanding of the outer solar system. But the spacecraft's 4-year primary mission was, in hindsight, only ever the opening chapter. Rather than shutting down once its planetary flybys were complete, Voyager 1 simply kept going, its trajectory carrying it up and out of the plane in which the planets orbit, on a one-way journey toward the absolute edge of the solar system and beyond. On August 25th, 2012, Voyager 1 crossed the heliopause, the invisible boundary where the constant outward pressure of particles streaming from the sun finally gives way to the vastly larger, colder, emptier medium of interstellar space itself, becoming the first human-made object in history to operate directly within the space between stars. It has been out there ever since, the single most distant object humanity has ever built. And on November 18th, 2026, it is projected to cross a genuinely staggering symbolic milestone, becoming so far from Earth that its radio signal traveling at the literal speed of light will take a full 24 hours, an entire day, just to make the one-way trip home. None of that distance would matter, of course, if Voyager 1 had no way to power its instruments, its computers, and the radio transmitter that allows it to keep talking to Earth at all. And this is where the spacecraft's entire, slow-motion, decades-long crisis actually originates. Out at Jupiter's distance from the Sun, let alone billions of miles further out in interstellar space, sunlight becomes far too weak and diffuse for conventional solar panels to generate meaningful power, which is precisely why NASA engineers in the 1970s equipped both Voyager spacecraft with radioisotope thermoelectric generators, commonly abbreviated as RTGs, compact nuclear devices that generate electricity not through fission or any kind of controlled reaction, but simply by capturing the steady heat given off as a chunk of radioactive plutonium-238 naturally decays over time, and converting that heat directly into usable electrical current. It is an elegantly simple, remarkably reliable piece of engineering with virtually no moving parts to break down over the decades, which is a large part of why Voyager 1's RTGs are still generating usable power today, nearly 50 years after launch, long after most conventional spacecraft components would have failed entirely. But the underlying physics of radioactive decay comes with an unavoidable, unforgiving catch. Plutonium-238 has a half-life of roughly 87.7 years, meaning its rate of heat production and therefore its electrical output declines steadily and permanently over time, with absolutely no way to reverse, pause, or refuel the process from Earth. At launch in 1977, Voyager 1's RTGs produced roughly 470 watts of usable power, enough to comfortably run all 10 of its original scientific instruments simultaneously alongside its cameras, computers, heaters, and radio transmitter. As of 2026, that output has fallen to somewhere under 270 watts. And the decline continues at a remarkably steady, remarkably relentless rate. of approximately 4 watts lost every single year, a number so small it sounds almost trivial, right up until you realize it has been compounding year after year for essentially half a century. NASA's mission engineers have known about this slow, mathematically inevitable decline since before Voyager 1 even left the launch pad. And the entire history of the mission since roughly 1980 has been an extended, increasingly difficult exercise in triage, deciding which of the spacecraft's 10 original scientific instruments to sacrifice, and in what order, to keep the overall mission alive for as long as humanly possible. The very first casualty came remarkably early, when Voyager 1's photopolarimeter system was switched off in 1980, shortly after the Saturn flyby, due to degraded performance rather than a purely power-driven decision. The pace of deliberate power-saving shutdowns accelerated considerably in the decades that followed. The plasma science instrument, which had helped study the solar wind, was turned off in 2007, again due to degraded performance, combined with the ongoing need to conserve power. Then, on February 25, 2025, NASA engineers made the difficult, deliberate call to switch off Voyager 1's cosmic ray subsystem, specifically to save power, an instrument that had spent decades helping researchers understand the high-energy particles bombarding the spacecraft from both the sun and from far outside the solar system entirely. By early 2026, that long, careful campaign of triage had already left Voyager 1 running on just a handful of surviving instruments, and the spacecraft's aging power system was about to deliver its most serious scare yet. On February 27, 2026, during what should have been a completely routine, previously planned roll maneuver, something happened that mission engineers had not fully anticipated. Voyager 1's power levels dropped unexpectedly, falling further and faster than the team had modeled for that specific operation. The danger this created was immediate and genuinely serious. If power levels had continued falling even slightly further, they risked triggering the spacecraft's own automated undervoltage fault protection system, essentially an onboard safety mechanism designed to shut down various components entirely on its own initiative in order to protect the spacecraft from a catastrophic, uncontrolled power failure. On paper, that kind of automatic self-protection sounds like a reasonable safety net. In practice, for a spacecraft nearly 15 light hours from Earth, it represents a genuinely alarming scenario, since recovering a spacecraft that has triggered its own automatic emergency shutdown from that distance is an extraordinarily lengthy, complicated, and risky process, one that offers no guarantee of a full or even partial recovery. Rather than risk the spacecraft's own fault protection system taking that decision entirely out of human hands, the Voyager mission team made the difficult call to act first, deliberately, on their own terms. As Voyager mission manager Kareem Badarudin put it plainly in NASA's own announcement of the decision, while shutting down a science instrument is not anybody's preference, it was, given the circumstances, simply the best option available. And so, 7 weeks later, on April 17, 2026, the command finally went out to power down the low-energy charged particles instrument, buying the spacecraft what engineers estimated would be roughly 1 additional year of stable operation. What makes this particular shutdown genuinely different from the long string of instrument deactivations that came before it is not the loss itself, painful as it clearly was for a mission team that has spent literal decades of their careers keeping this specific spacecraft alive, but rather what NASA is racing to build in the year of breathing room that shutdown is meant to buy them. Mission engineers are currently finalizing an unusually ambitious, genuinely high-stakes power management strategy that they have nicknamed, with a dash of dark institutional humor entirely fitting for a team that has spent half a century fighting a slow-motion battle against the laws of thermodynamics, the Big Bang. Rather than simply shutting down individual components one at a time as power continues its inevitable decline, the Big Bang procedure would involve a single, coordinated, simultaneous reconfiguration of the spacecraft's entire electrical system, deliberately switching off a specific group of higher power devices all at once while, at the very same time, activating a separate set of lower power alternative components designed to perform many of the same essential functions, using dramatically less electricity. The core engineering challenge underlying the entire maneuver is not simply about keeping scientific instruments running, but about something even more fundamental to the spacecraft's basic survival. Voyager 1's onboard heaters exist to keep its critical internal systems, most importantly its fuel lines, from freezing solid in the brutal, near absolute zero cold of interstellar space. If those fuel lines were ever to freeze completely, the spacecraft would permanently lose its ability to fire the small thrusters that keep its high-gain antenna precisely pointed back toward Earth. And once that pointing accuracy is lost this far from home, NASA's ability to communicate with Voyager 1 at all would almost certainly end forever, regardless of how much electrical power technically remained in its aging RTGs. The Big Bang, in other words, is not primarily about squeezing out a few more months of scientific data. It is about preventing the specific, permanent failure mode that would end the entire mission outright. Given the enormous risk inherent in attempting such a sweeping, simultaneous reconfiguration on humanity's single most distant and most historically significant spacecraft, NASA's engineering team made a deliberately cautious choice about exactly where to test the procedure first. Rather than risking the maneuver immediately on Voyager 1 itself, the team planned to first attempt the Big Bang fix on its twin spacecraft, Voyager 2, which, despite having endured its own long history of instrument shutdowns, including the deactivation of its own cosmic ray subsystem back in March of 2025, currently retains a somewhat larger power margin and sits meaningfully closer to Earth, making it the comparatively safer test subject for an inherently risky one-shot maneuver. Those initial tests were scheduled to run through May and June of 2026, and if the procedure proved successful on Voyager 2 without triggering any unexpected complications, the team planned to attempt the same fundamental fix on Voyager 1 itself no earlier than July of that same year. There was even a genuine possibility, mission engineers noted, that a successful Big Bang procedure could allow them to eventually restart the very same low-energy charged particles instrument they had just been forced to switch off in April, a detail reflected in the engineering itself, since NASA deliberately chose to leave a small motor that spins the LECP sensor running rather than shutting the entire device down completely, specifically to preserve the option of bringing the instrument back online later if the Big Bang procedure freed up enough additional power to make that possible. As of the spring and summer of 2026, following the April shutdown of the low-energy charged particles experiment, Voyager 1 has been left operating with just 2 functioning scientific instruments out of the original 10 it carried at launch nearly half a century earlier. The first of those 2 survivors is the magnetometer, commonly abbreviated as MAG, which continues measuring the local magnetic field surrounding the spacecraft as it drifts deeper into interstellar territory that no other human-made object has ever directly sampled. The second is the plasma wave subsystem, or PWS, an instrument capable of detecting plasma oscillations and other subtle radio frequency signatures that allow scientists back on Earth to indirectly calculate the density and behavior of the extremely thin ionized interstellar gas the spacecraft is currently traveling through, data that has already produced genuinely significant scientific results, including a landmark 2021 research paper led by astronomer Stella Ocker documenting persistent plasma wave emissions detected by Voyager 1, evidence that has helped researchers trace variations in interstellar plasma density across a region of space that remains, even now, almost entirely unexplored by any other operating spacecraft. These 2 remaining instruments represent, in a very real sense, humanity's only continuously operating scientific eyes and ears in true interstellar space, and protecting their continued function, even at the cost of everything else the spacecraft was originally built to measure, has become the singular, overriding priority driving every single power management decision the Voyager team now makes. The instruments themselves represent only part of the ongoing power-saving campaign, because scientific sensors are far from the only systems drawing electricity aboard an aging spacecraft this deep into its operational life. Alongside the string of instrument deactivations stretching back to 1980, NASA's engineering team has also been forced to systematically shut down individual heaters, warming various spacecraft components once believed absolutely essential, gradually turning off backup systems and redundant hardware that had simply never been needed given how reliably the spacecraft's primary systems continued functioning decade after decade, and even reducing the precision of certain onboard instruments in ways that saved marginal amounts of power at the cost of slightly reduced data quality. Perhaps most strikingly, mission engineers have also repurposed small amounts of power originally reserved as backup safety margin for entirely different subsystems, essentially betting that certain categories of onboard failure had become unlikely enough, after so many decades of F-stable operation, that the safety margin protecting against them could be safely redirected toward keeping the spacecraft's remaining functional systems alive instead. This entire strategy carries an inherent, unavoidable tension that mission engineers have had to navigate carefully for years now, since every watt of power redirected toward keeping an instrument or a heater running is, by definition, a watt no longer available as a safety cushion. In the event something else aboard the aging spacecraft unexpectedly goes wrong, that tension became vividly, alarmingly real in late 2023 and into 2024, when Voyager 1 suffered what remains, to date, the single most serious technical crisis of its entire near 50-year mission. A full communications breakdown rooted not in the spacecraft's dwindling power supply, but in a corrupted memory chip aboard its flight data system, the onboard computer responsible for packaging science and engineering data before transmission back to Earth. For roughly 5 months, Voyager 1 transmitted nothing back to mission controllers but unreadable, garbled static, a signal indicating the spacecraft was technically still alive and still listening, but functionally incapable of sending home any usable information whatsoever, an outcome many engineers privately feared might mark the effective, unrecoverable end of the mission after nearly half a century of continuous operation. JPL engineers eventually traced the problem to a single corrupted memory chip representing roughly 3% of the flight data. System's total memory capacity, and in a remarkable feat of remote software engineering, performed across a communication delay stretching to roughly 22.5 hours each way, the team devised a way to rewrite and relocate the affected code into different, functioning sections of the computer's remaining memory, restoring full, usable communication with Voyager 1 by the following spring. That crisis, distinct as it was from the ongoing power decline now dominating the mission's final years, offered a preview of exactly the kind of high-stakes, no-second-chances engineering problem-solving the current Big Bang power strategy now demands. A reminder that keeping this particular spacecraft alive has, for years now, meant solving genuinely unprecedented technical puzzles with absolutely no possibility of a physical repair mission and no room whatsoever for error. Both Voyager spacecraft carry, bolted to their exteriors, an object that has become far more culturally famous than almost any single piece of scientific data either probe has ever returned. The Golden Record, a gold-plated copper phonograph disc containing a carefully curated selection of sounds, images, spoken greetings in dozens of human languages, and musical recordings intended to represent the diversity of life and culture on Earth, assembled under the direction of astronomer Carl Sagan specifically, for the remote possibility that some future spacefaring civilization might one day encounter either spacecraft drifting silently through interstellar space, long after both probes have gone permanently dark, and long after the humans who built them are gone. That record requires no power whatsoever to exist, no functioning instrument, no active transmitter, no remaining watt of electricity from a decaying RTG, since it was designed from the outset to persist as a purely physical, entirely passive artifact, capable of surviving for potentially billions of years in the near-perfect vacuum of interstellar space, dramatically outlasting every single electronic system currently keeping Voyager 1 in contact with Earth. In a very real sense, the Golden Record represents the part of the Voyager mission that was always designed to continue long after the countdown currently consuming so much of NASA's engineering attention finally reaches zero, a strange kind of built-in acceptance, baked into the mission from its very conception in the 1970s, that someday the instruments would fail, the power would run out, and the conversation between Voyager 1 and the people who built it would end, even as the spacecraft itself kept drifting onward, carrying its silent cargo, essentially forever. Voyager 2, meanwhile, offers mission engineers a useful, if imperfect, point of comparison for understanding just how differently this slow-motion power crisis can unfold, depending on a spacecraft's specific trajectory and configuration. Launched slightly before its twin, but following a longer, more circuitous path that included flybys of Uranus and Neptune, Voyager 1's trajectory never brought it near. Voyager 2 did not cross into interstellar space until November of 2018, 6 years after Voyager 1 achieved that same milestone. Despite that later crossing, Voyager 2 has followed a broadly similar pattern of instrument sacrifice, including the March 2025 shutdown of its own cosmic ray subsystem and its current position, somewhat closer to Earth, and carrying a marginally more forgiving power margin than its twin, made it the mission team's chosen test subject for the riskiest phase of the entire Big Bang procedure. Whatever happens to Voyager 2 during those critical tests in May and June of 2026 will directly shape exactly how and exactly when NASA's engineers ultimately attempt the same maneuver on Voyager 1 itself, meaning the fate of humanity's single most distant object currently depends, in a very direct and immediate sense, on how successfully its twin sibling, launched from the very same Florida launch pad within weeks of Voyager 1 back in the summer of 1977, weathers an entirely untested engineering procedure nearly 50 years later. The ultimate goal driving all of this careful, painstaking engineering triage is not simply to keep Voyager 1's transmitter faintly humming for its own sake, but to reach a specific, deeply symbolic milestone the mission team has been quietly working toward for years. As Suzanne Dodd, the longtime program manager for the Voyager mission at JPL, put it in comments shared with Smithsonian Magazine, her personal goal has always been to see a spacecraft that actually celebrates its 50th anniversary from launch, a target Voyager 1 would reach in September of 2027, and one the team's current strategy, buying incremental extra months through individual shutdowns while racing to implement the far more ambitious Big Bang procedure, is specifically designed to help the spacecraft survive to see. Beyond that 50th anniversary, The team's stated ambition stretches even further, hoping to keep at least one functioning scientific instrument operational aboard both Voyager spacecraft well into the early 2030s, squeezing every conceivable extra watt and every extra month of usable data out of a power source that is, by the unbreakable laws of nuclear physics, guaranteed to eventually run out entirely, with no possibility of resupply, repair, or replacement across the entire multi-billion-mile gulf separating the spacecraft from the planet that built it. What makes this entire unfolding story so quietly, unexpectedly moving, far beyond its purely technical details, is the specific nature of what is actually being lost each time another instrument goes dark. Voyager 1 is not failing because any critical component broke, malfunctioned, or wore out through simple mechanical fatigue, the way most aging machinery eventually does. Every remaining system aboard the spacecraft, by every account from the engineers who monitor it daily, continues functioning essentially as designed nearly half a century after launch, a genuinely remarkable testament to the quality of 1970s-era aerospace engineering. Voyager 1 is instead being slowly, deliberately, unavoidably switched off, piece by piece, by the very team most desperate to keep it alive, forced into an extended, increasingly painful series of sacrifices, by nothing more dramatic or preventable than the simple, patient, mathematically certain decay of plutonium atoms, ticking down at exactly the same steady rate they always have, utterly indifferent to how much humanity might wish they would slow down. Somewhere out past 15.8 billion miles of empty, freezing darkness, carrying its famous golden record of Earth sounds, images, and greetings intended for any other space kind that might someday encounter it, Voyager 1 continues sending back its faint, patient signal, now measured in an ever-shrinking list of instruments and an ever-tightening power budget, on a countdown that NASA's engineers have been fighting brilliantly and stubbornly for nearly 50 straight years, and one that every single person currently working on the Voyager mission understands with complete scientific certainty they will eventually, someday, finally lose.